Hi guys, so today in lieu of me being in the classroom, I'm instead writing a midterm and a benchmark for my algebraic reasoning class, and my husband is there, and as much as I would love to say that he could teach you and give you a good day 2 review of day 1's notes on long division, I just don't think it's going to happen. So that's going to be me, and I'm going to try to do this. I've got someone right here by me who may or may not interrupt me. I'm hoping she doesn't. And I'm going to try to go fast. I already did this once, and it was 27 minutes long, and I don't want you to have to listen to me for that long. So if you look at this problem, it says divide. That's all it says. So it really doesn't matter which method you use. You may have your preferred method, and if you do and you want to use that, great. I'm going to use synthetic because this is a linear term right here, and I can very quickly do the division problem. If you recognize that the factor is r plus 3, that means the root or solution that we would be dividing by is negative 3. And so I'm going to put that in the corner like I always do, and I'm going to write all the coefficients here and the constant that are in order, descending order, starting with the highest power down to the constant. There are no missing terms in here in this problem, so I can with confidence not have to worry about putting a 0 in for anything like we did yesterday. It could happen again today, but it's not going to happen on this problem. Don't forget, the first thing we always do is bring down, this is our leading coefficient, the coefficient in front of our highest powered term. And once we do that, we start the process of multiplying. We're always multiplying the negative 3 times the newest number that's been put down below. And when we get that product, we write it in the next column and we add. We're going to multiply negative 3 times this newest number in the bottom. That gets us 27. We're going to add. We get negative 7. We'll multiply by negative 3 again. That gives us 21. We add. We get 4. Negative 3 times 4 is negative 12. We add, we get negative 2, and one more time, negative 3 times negative 2 is a positive 6. We add, and we get 7. So we have our answer. We just have to write it in a polynomial way with x's. This is our remainder. This right before our remainder is our constant. This would be our linear, like our, in this case, r to the first power coefficient. This would be our quadratic coefficient. We didn't do this yesterday, but we may get up into cubics, and even above that would be a quartic. We talked about what a quartic was. So this means that our first answer, the first part of our answer is going to be an r to the 4th power. I don't have to write the 1, but I can. And then we'll go from there, descending in power until we get to our constant. And after our constant, we will write whatever our remainder is. And remember that we have to write it over what we divided by, which really, a negative 3 just helped us do the problem. What we were really dividing by with an r in it was that factor. So that is why our remainder looks like that. And we are done with our problem. Let's try that again on the next problem. We have b's this time. And notice that we go from a 5th power to a 4th to a 3rd. We skip a 2nd power, 1st power, constant. So when we're writing our line, we're going to have to make sure to hold a place for that b squared term that is missing here in case he turns up in our answer. So first of all, we got to make sure we know what we're dividing by. If b plus 2 is a factor, that means the number that we're going to use as a root in this problem in that corner slot is a negative 2. You can either just change this sign, or you can set this equal to 0. Either way, you'll get a negative 2 is what we should be putting in that box. And we're going to write our coefficients in descending order, starting with the b to the 5th, that was a 1. The b to the 4th coefficient is 8. B to the 3rd is 12. B squared is missing, so we're going to put a 0 there. Our linear is negative 4, and our constant is negative 18. We're going to draw a line across, we're going to bring down our leading coefficient, and we're going to start multiplying and adding. We're always adding these two that are in the same column together. Negative 2 times 6. We add, in that case we get 0. Negative 2 times 0, still a 0. Added, still a 0. Negative 2 times 0 is still a 0. Finally, we get out of 0 world. Negative 2 times negative 4 is 8, and we end up with a remainder of negative 10. So we're pretty much done. We just have to rewrite this in a polynomial form. When you have zeros here, it means I'm not going to have a linear part to my answer. And even before that, I'm not going to have a quadratic part to my answer. I will have a cubic part and I will have a quartic part. And I'm going to skip these two. I'm not going to write these in my final answer. It shows that they're missing. So I have a 1x, in this case it's a b, sorry, not an x, b to the fourth with a 1 in front of it if you want or not, plus 6b to the third. I'm going to skip a second power. I'm going to skip a first power. I'm going to go straight to the constant. And then as always, when I have a remainder, I always put a plus. Put your remainder amount over what you divided by. Your divisor was b plus 2. And that is my answer. And we're done with that problem. Now if we look at number 3, we have a fifth power, fourth power, third power, second power, linear, first power term, and constant. Nothing is missing out of this dividend. This is our divisor, and it's linear, so we can use synthetic again with this, but we need to set that equal to 0 and solve for k. If there's a coefficient in front of k, it's not quite as easy to just switch the sign. I'm sure a lot of people could solve that in their heads, but if you can't, we would just solve for k, and we would get that the k value, the solution or the root or the 0 to this problem is 2. So 2 is what goes in a corner, and we'll write our coefficients all the way across. Remember that if there's a minus, you have to put it in as a negative in synthetic. If you neglect a minus sign down here, you will not get an answer that is right. And again, we bring down our leading coefficient, and we start our multiplying pattern and our adding pattern. Multiplying, adding, multiplying, adding, multiplying, adding, and multiplying, and adding. And this is what we end up getting. That is our remainder position. Before that is where our constant is, our linear coefficient, our quadratic coefficient, our cubic, and our quartic. So I know that my problem, remember these are k's, I'll start with a 4k to the fourth because that's what a quartic would be, followed by a cubic term that has a negative 36 in front of it. This was that's supposed to be a positive 4. Positive 4 k squared. A positive 16k, a minus 32 for the constant, and then we will have a remainder that is negative 5 over what we divided by, which was the 4k minus 8. And that is our answer. Hopefully that makes sense. All of those pieces, you can see how they relate to each other in the final answer. So we've practiced our synthetic now 3 different times. None of them were nice, neat, beautiful problems that had no remainder, but we can handle that. And if we look at number 4, there is a little bit of a difference here. This is not being divided by something linear. This is being divided by something that is quadratic. That means synthetic division is not an option for us. So we're going to set this up as a polynomial long division problem, which is good review. We can use the practice. This is what's going to go inside. This is our dividend up here, and this is our divisor. Now notice before we set it up, is there anything missing out of the dividend? It goes from a fourth power, third, second, linear, constant. There is nothing missing in our dividend. So I can go ahead and write, to kind of start my problem with this. Looking exactly like it looks. Now when I write my divisor on the outside, I'm going to notice that this goes straight from a quadratic term down to a constant. It's missing just a regular x. You don't have to do this, but I think it helps us to see that we're missing an x so that we keep everything aligned the way we like it to be. Because I think polynomial long division we're okay with as long as everything is aligned and in the order that we're used to seeing it. So I'm going to go ahead and put that there, even though I know that it's not technically there, to see if that helps us as we're making order of our polynomial long division problem. So remember, when we start our division problem, we are looking at this leading term, and this is the only part that we are interested in the dividing step of these polynomials. So you can either do that in your head, what does 8x to the 4th divided by 8x squared, or you can write it off to the side. That's perfectly legitimate. And what is the answer to that division problem? It's a quadratic, x to the 2nd power. So I'm going to go find, I like to put my like powers above like powers. So my x squared will go here, and it's now time to multiply this times each of these 3 terms and put the answer underneath in those 3 places. So x squared times 8x to the 2nd is 8x to the 4th. We were hoping to see that. X squared times 0x means 0x to the 3rds, and x squared times 3 is a positive 3x squared. Don't forget, we're subtracting these, and when we subtract, we have to change the signs in front of that second row. That's the only way to properly subtract polynomials together. You have to change the signs of the things that are being subtracted. So this is going to cancel out. I had negative 24x to the 3rds, and I did not change that with the 0. And I had negative 21x squared, and I have negative 3 more of them. So now that's going to be a negative 24. And then you always bring down your next term. We haven't used it yet. So we are now interested in this term divided by this term. So again, you can write that out to the side if you need to and figure out what that should be. It should be a negative 3x. So that's what I'm going to march over here and put on top of the other linear term. And I'm going to ignore this x squared. We're done with it. We are focused now on this negative 3x and multiplying it properly to each of these 3 things. So we have negative 24x to the 3rd. We have a negative 3x times 0x is a 0x squared, and negative 3x times 3 is a negative 9x. And we are going to subtract those, meaning I'm going to have to change the signs. 0 doesn't really have a sign, so we don't have to worry about that. That's going to cancel out the cubics. These 2 will combine to be negative 24x squared, and these 2 will combine to be negative 72x. Don't forget, we have not used our last term yet in the original dividend, so we got to bring that last term down, and we're ready to do one final division round. We know that because this power is still equal to or higher than this power. We keep going until this no longer has as high a degree as this does. And so when we divide these 2, the x squareds cancel out, and we just have negative 3. I'm going to bring that up here. That's a negative 3. Sorry, it looks kind of like a 2. And I'm going to take negative 3 and I'm going to multiply it to these 3 things and see if we have a remainder. And when I do that, of course, I'm still fiddling with that sign. It doesn't matter. We're going to change the signs of all of these bottom ones. And we get negative 72x minus 14. And I know I'm done because I've written my constant. That's always the last thing in my actual division problem, unless we have a remainder, and we do have a remainder. So my final answer, all the things that went in evenly into the dividend, and then this big, ugly remainder. And when you write your remainder, that divisor that did not have that linear term, you don't have to write that in there. You can write this original, prettier one. This is my answer. So that's kind of reviewing polynomial long division. Some of you guys actually preferred that from yesterday, so you get another crack at it. You could have done polynomial long division on all of these at the top. You still should have gotten the same answers that we did. So let's flip to the back. Another thing that you could be asked to do, and this is something we haven't done yet, but it's super easy. It says state if the given binomial, and this is the binomial that they're talking about, and here too. State if it is a factor of the given polynomial. Okay, we know how to find factors. I mean, can we look at the number 24 and say, is 2 a factor? Well, for you to answer that, you just see, well, does 24 divide by 2? Yes, it does. So yes, that is a factor. That's exactly how we're going to handle this down here. We're going to use, I would use synthetic division, but you can use long division if you want. That's a lot of work, but you can. I'm going to see if this factor which as a root or solution or 0 would be -8, I'm going to see if it divides into this polynomial with no remainder. If there's no remainder, then yes, it's a factor. Okay, so I'm going to set up a synthetic problem. I go from a third power, second power, first power constant, so I don't have any missing pieces that I have to make room for. And I'm going to bring down, and I'm going to multiply, and I'm going to add. And our hope is that if this is a factor, we would see a 0 at the end of this problem. But we don't. It has a remainder. So any remainder that's not a 0 means this is not a factor. This is not a factor of this polynomial, so we put no. We put no because there's a remainder there, and there's supposed to be none if it's actually a factor. So this does not divide evenly into this. Let's try it again with this one. We have a binomial that as a factor is x plus 7. As a solution or root or 0, it's -7. So we are going to put -7 in the corner. Let's look. We have an x to the 4th, an x to the 3rd, an x squared, an x to the 1st, and a constant. So they're being so nice to us. Nothing missing. So I don't have to worry about putting a 0 in place of something that's missing when everything's there. And I'm going to bring down my leading coefficient, and I'm going to multiply, and I'm going to add. Multiply and add. Multiply and add. Multiply and add. Hey, look! No remainder. If we get a remainder of 0, this is a yes. This is a factor of that polynomial. This piece right here, we're going to worry about after Thanksgiving, so you can cross that out. And I think on your assignment that we'll give you today, if it asks you to do more than just state if it is a factor or not, you can cross that out for now. We will get there, but we're just not there yet. So the last thing that we're going to do is a word problem. You know that we'll always have some way to apply this concept to real life. And this is about a clock factory, and they make profit. That's what you hope to do if you're a company, right? Profit P in millions of dollars for a clock factory can be modeled by this expression that the profit is equal to -13x cubed plus 21x. X stands for the number of clocks produced in millions. So the company now produces 1 million clocks and makes a profit of 8 million. Remember, P is our output. It's like our Y value. And it says that the number that we see for that stands for millions. So I don't have to write 8 million with 6 zeros after it. This represents 1 million clocks. This represents 8 million in profit. Okay, so we've been given a point. We know that when they produce 1 million clocks, they're likely to make 8 million in profit. They would like to cut back on production, meaning they don't want to make that many clocks. That's a lot of work to make $8 million. They want to cut back. What is a lesser number of clocks that could produce the company the same amount of profit? This was a cubic, right? So, and it's a negative cubic, so it looks something like this probably, just a sketch. The $8 million mark may hit at more than one place. So we know that if they make 1 million clocks, they'll make this 8 million, they'll hit this line. But are there lesser values that will also achieve an $8 million profit? That's our goal. We want to eliminate this one out of there. And that will knock this down by a degree. And then we'll have a quadratic that we can solve. We have lots of ways to solve quadratics. So what we're going to do is we are going to set this equation equal to the profit that they just gave us, which is our goal of 8 million. That's what we want to make, 8 million. Now, we can't do anything with that until everything is on one side. So I'm going to rewrite it to look like this. And I know that 1 million works in this equation. So I know that 1 is something that I can divide this by. And in the process of doing that, I'm eliminating one of my powers. So this is 1 million But our goal is in setting this up, we're going to end up with a quadratic that we can actually solve and get those other two values that also get 8 million. So I'm going to write this out. I have a third power. I have no second power. So I'm going to put a 0 here. I have a linear term and I have a constant. And I know that this is going to work already because I already know 1 million is going to get me, 1 million clocks made is going to get me 8 million. So I'm expecting no remainder. So if we do our synthetic division steps here where we're adding and multiplying, we do see that we end up with a 0 remainder. So we have no remainder, but we have this quadratic left over that looks like this. Can I solve and get solutions for x when I'm down to a quadratic? Yes. We could try to factor. We could try to complete the square. Neither of those look like good options to me with these funky numbers right here. So remember, quadratic formula is always an option. And we taught it to you so that when we got to this point, you would be able to apply it with not too much anxiety. But we're going to put the opposite of b right here. B is this middle term. It's a negative, so the opposite of it is a positive. I'm going to take that b value of negative 13 and I'm going to square it, which would give me 169 minus 4 times a times c all over to a, which was a negative 13, right? Now, if I simplify this, and I know that you may not have your calculators in front of you, but you will always have a 4-function calculator available, so you can just trust me on my math here. This ends up being 585, and the square root of 585 is about 24.2. I have two solutions here. I have one that's 13 plus 24.2 over negative 26. But I can guarantee you that that is going to get me a number that makes no sense in this problem. Can I produce negative 1 million clocks? No, that's extraneous. So I'm not going to pay attention to that solution. That doesn't make sense. I'm going to do the other solution, which is to take away 24.2. And when I get that, I get this answer. That means not even a 500,000 clocks will still get me $8 million. Would you like to work less and still make the same amount? I know I would. So 0.43 million is approximately 430,000 clocks. So instead of breaking their tails, busting their tails, and having to make 1 million clocks to earn $8 million in profit, they can do this instead. I'll take that any day. So I hope you guys understood this. Replay it if you need to. I'll put it on Canvas. And Daisy says good night.